Hi everybody and welcome to a new exciting video in the audio signal processing for machine learning series. Last time we looked at the theory behind a few frequency domain audio features. This time I'm going to implement one of those from scratch in Python, and the one that I'll be implementing is called band energy ratio. I'm not going to get too much into the theoretical details of this because I've done this like in the previous video. So if you find yourself not understanding what I'm talking about, just go back to my previous video, which should be over here. Okay, so let's take a look at this notebook, and as you can see, I've already implemented some code, and that's because this is like stuff that we've seen multiple times throughout like this series, and I didn't want to spend time like typing this down. Okay, so the first thing that I do is I import some libraries that we'll need, then I load the audio file. So I have couple of audio files that I'll be working with today. So one is a Red Hot Chili Peppers song, and we've heard this time and again throughout the series, and the other one is a classical music piece by Claude Debussy. So let's quickly listen to this too. So yeah, this is a lush string driven orchestral piece by Debussy. And here we have the song by the Red Hot Chili Peppers. Okay, you get the idea, right? And so what I do next is just I load the audio files with a librosa using this librosa.load, and I get the waveform really, so like a NumPy array, and then the sample rate, which is defaulted to 22,050 hertz. And then, given we are working with frequency domain features, and band energy ratio is a frequency domain feature, what I want to do is just extract the spectrogram. And so how do I do that? Well, I just use once again a simple function from Librosa that's called librosa.stft, and I pass in a couple of constants, so the frame size and the hop size, and I obtain the spectrogram for Debussy and Red Hot Chili Peppers. Now, if you don't know what a spectrogram is, or like short-time Fourier transform is, I have a bunch of videos on these topics in this series, so I highly suggest you to go check out before like moving along with this video. Let's now move on to the cool stuff and start calculating the band energy ratio. So let me add a few boxes down here, and I'll use some markdown to say, yeah, calculate a band energy ratio. Okay, so let's take a quick look at the definition of the band energy ratio. So here we have the definition from the previous video basically. So, and here you can see that the band energy ratio at time t, so at a given frame, is given like by this formula here. So the key thing that we want to get as the first point is the split frequency F, capital F, because this is the one, if you recall, that's going to tell us, that's going to give us like the threshold that we'll use to say, okay, so all the frequencies above this frequency are belong to the higher frequencies, and all the frequencies below the split frequency belong to the lower frequencies. But now, obviously, we can pass in a continuous frequency, like in hertz, like 2000 hertz or 3000 hertz, but the spectrogram has discrete values, right? So it has discrete frequency bins. So we need to create a function that maps a continuous frequency onto the discrete frequency bins that we have. And so that's what we want to build now. So we'll define a function, and we'll call it calculate split frequency bin, like this. And this function accepts a few parameters. So first of all, it accepts a spectrogram, then the split frequency, and finally the sample rate. Okay, so now let's see what we should do here, like all the different steps. So as the first thing, what we want to calculate is the frequency range that we have in the spectrogram. In other words, so we want to ask ourselves, so how what's the frequency range that we are capturing in the spectrogram. And now to show you what I mean here, let's just go back and take a look at the, for example, at the BC spectrogram. So I want to just like take the shape here of this, and as you can see, like in the shape of this spectrogram is given by it's kind of like a two-dimensional array, right? And so on the first dimension we have 1025, and that is the number of frequency bins that we have, right? And so what we want to really understand is like, what does 1025 frequency bins like correspond to in terms of like frequency range? Okay, so and how do we do that? Well, this is like something that we can easily do, because we know that the spectrogram reduces its like frequency range from the sample rate. It moves on to the Nyquist frequency, and so we can obtain that by doing the sample rate divided by 2. The next logical step here is to calculate the delta frequency between two adjacent bins. So in other words, how much, so when we move, say, from frequency bin to number 3 to frequency bin 4, so how much do we actually move in the continuous frequency, right? And so we can do that by saying that the frequency delta per bin is equal to the frequency range divided by the total number of frequency bins that we have. And we can easily get that from the spectrogram. So we do spectrogram dot shape, and we take the first dimension. And the first dimension, as we saw, is equal to the number of bins that we have in the spectrogram. Okay, so now we know the frequency delta for each bin, and so we are now ready to calculate the split frequency bin. So the split frequency bin is equal to the split frequency, and this is given in hertz, and that's divided by the frequency delta per bin. In other words, what we're doing is we're mapping this continuous frequency, that's the split frequency, onto the closest frequency bin available. And but you may see here that given like we have two numbers, so the split frequency, the frequency delta per bin, it's likely that we're going to get like some kind of a float number. And obviously the frequency bins that we have are discrete, and that's the whole point of having like discretization here. So we can't take a frequency bin that's equal to 10.4. It doesn't make sense, right? So we have to move to an integer number. So we have to round up the number. So what can we do to round this up, round this number? So we can use the numpy.floor function. And what this function does, it's a form of rounding, and it always rounds numbers down. So for example, say I have 10.4, and then if I apply the floor, what I get back is 10. And I get it as a float number. If I have like 10.9, again, I'm gonna get 10.0 like this, okay? So here we have the split frequency bin. So now we can return it, but as I mentioned, this is a float number, so we want to cast it to an int. Okay, so this should be ready. So now let's try it. So we can say split frequency bin, and then we use this one. We calculate split frequency bin. So as the spectrogram, we just pass in the BC spectrogram. And then as a split frequency, we're going to be using 2000 Hertz, which is a totally fine split frequency. And as the sample rate, I'm going to use the default rebrowser one, which is 22,050. And now let's print this split frequency bin like this, and as you can see, okay, so the 2000 Hertz split frequency has been mapped onto this frequency bin, which is 185, which is 185 out of 1025 frequency bins that we have in the spectrogram. Okay, so with this knowledge, we can now move on and actually calculate the band energy ratio. So let's write the function here. So we'll do that definition with define calculate band energy ratio. And this function gets three parameters once again. So it gets the spectrogram, it gets the split frequency, and the sample rate. So, and obviously these are the same that we are using in calculate split frequency bin. Okay, so the first step is to actually get the split frequency bin, right? And so we can easily do this by using our newly implemented function. So we'll call calculate split frequency bin, and we'll pass in all of these arguments, and that function will be so nice as to give us back the expected split frequency bin. Okay, so now the next thing that we want to do is to move to the power spectrogram. Okay, and why do we do that? Well, we do that because, as you can recall, probably like from this formula from last video, or just like looking at it now, we are interested in the power spectrograms here. So this MT of n squared is basically like the magnitude spectrogram. So it's kind of like the power spectrogram, right? Because we are taking the magnitude spectrogram here for a given frame at a given frequency bin, and we are squaring it, which basically means we are moving from the magnitude spectrogram from the magnitude to the power. Okay, and so rather than calculating this power at each point in time and frequency bin, we'll just like calculate it once initially. So what I want to do, as I said, is like move to the power spectrogram. And so how can I do that? Well, this is quite simple, because we start from the spectrogram, which has complex values, and we apply the absolute value to that. And so we'll do an numpy.abs, and I'll pass in the spectrogram. And if we did only this, we would have the magnitude spectrogram. But now we are going to be squaring this so that we can get the power spectrogram. Now, there's another trick that we need to apply here. And that's because we're going to be calculating the band energy ratio at each frame. So we want to iterate through the power spectrogram and be able to iterate like frame by frame. But now, if you take a look at the spectrogram like this here, you'll see that the shape is given by, it's a two-dimensional array. But the first dimension is the frequency dimension, and the second one is the time dimension. So in other words, here we have like the number of frequency bins, and here we have the number of frames. Now, if we want to iterate through this the spectrogram or the power spectrogram based off time, so what we need to do is just like get the so-called transpose of this thing here of the spectrogram. And so how can we do that? And that's very, very simple. So let me just like get this and say wspec transpose, and this is equal to wspec dot capital T. And this will give us the so-called transpose of the spectrogram or of a matrix or an array. So, and now if we take a look at the shape here, you'll see that what happened was kind of like the inversion of these two dimensions. So now I have the the time dimension first, so the number of frames, and then I have the frequency as the second dimension. And this is what we want to do on our power spectrogram. So we'll do like this. So power spectrogram is equal to power spec dot capital T. And so this way we just get the transpose of the power spectrogram. Okay, so now let's create a variable like this. So an empty list like this, and this is where we'll cache the band energy ratio for each frame. And remember, the band energy ratio as a feature is a frame-based feature. So we're going to have a value of band energy ratio for each frame. So, and we'll be caching it for each frame here, like in this variable called band energy ratio here. Okay, so we'll do now. I will iterate through all the frames in the power spectrogram. And so we'll do for frequencies in frame in power spectrogram. So what should we do here? Well, so here we are iterating through all the frames and getting like the value like of the for each frequencies, right? Like for each frame. In other words, what we want to do here is calculate the band energy ratio for each frame. So let me put a path for the time being. And so what should we do here? Well, it's quite straightforward. So what we want to calculate is like these two items. So the numerator and the denominator. So the numerator is basically the sum of the power in the lower energies, and the denominator corresponds to the sum of the power in the higher frequencies. So let's do that. So we'll do sum power low frequencies. And how do we calculate this? Well, we can use numpy.sum, and then we'll pass in the frequencies in frame here. But we want sum across all the values, or across all the frequencies, but rather just take the first frequency bins up to the split frequency bin. Okay, so and it's going to be easy to do the same thing for the high frequency, but so let me just like rewrite this as high. So sum power high frequencies, and so here we'll sum the values, all the values for the power at all the different frequency bins in the higher part of the spectrum. And so what this actually means is that we'll slice this starting from the split frequency bin and then go up to like the last frequency bin, the highest frequency bin. Okay, so now with this we have both of the elements, so the numerator and the denominator here in this formula. So what remains to do is just like to divide this. Okay, so we'll do that. The band energy ratio current frame is equal to the sum power of the low frequencies divided by the sum of the power for the high frequencies, like this. Okay, so the next step here is to just append the band energy ratio for the current frame to the band energy ratio list here, so that we can catch the value of the band energy ratio for the current frame. So we'll do a band energy ratio dot append, and we'll pass in the band energy ratio of the current frame like this. Okay, so now we are ready to return, and I'll just cast this list to a NumPy array. So I'll do a NumPy dot array, and we'll pass the band energy ratio like this. Okay, so now let's see if this works. So what I want to do is to get the band energy ratio for Debussy. And so the way I'll do this is I'll call the calculate band energy ratio, and I'll pass in the spectrogram, and the spectrogram here is going to be this Debussy spec. Then I'll need to specify the split frequency. So the split frequency will be using 2000. That, as I said, is a totally fine split frequency. And then for the sample rate, if you remember, guys, like when we loaded the waveform here, we got back like the sample rate that's defaulted to 22,050, but I'll get like this SR over here, like this. Okay, so now let's take a look at the band energy ratio shape. Let's take a look at this. Okay, so this is a NumPy array which only like one dimension, and it has 1,292 items in it. And is it correct? Well, it is correct, because if you guys remember here, like in the spectrogram we had well, this is the transpose spectrogram. So here, like in the first dimension, we have the time dimension, which is equal to 1,292, which is the same number for the band energy ratio array. And that basically means that we're getting like values for all the different frames that we have in the spectrogram, which is what we were looking for. Okay, so now let me do the same thing. So let me also get the band energy ratio for the Red Hot Chili Pepper, Red Hot song. And so here, obviously, I need to pass the Red Hot spectrogram. Okay, good. Okay, so the last thing that now remains to do is to actually visualize this band energy ratio curves. And I also want to compare these two so that we can draw some conclusion about band energy ratio curves in different genres, like in this case, rock music and classical music. Okay, so now, first of all, let me add a few blocks like this, and then I'll, well, not that. I want the markdown, and I'll say visualize band energy ratio curves. First thing we want to do is create a figure. So we'll do plot.figure, and I'll pass a fig size, and I'll set this to 25 by 10 like this. Okay. So next we want to create a plot. So we'll do plot.plot. And here we should pass three things. So the value for the x-axis, which is going to be time for us, and then the value for the y-axis, which is the actual band energy ratio array, and then an optional color so that we can identify the two different curves for the Debussy stuff and for Red Hot Chili Peppers song. Okay, so let's do the first thing. So we'll pass t. Now, t doesn't exist yet, so but for the time being, I'll put it there as a placeholder. Then I'll pass the band energy ratio for Debussy as the y-axis, and then for the color, I'll say blue for Debussy. Okay, so we'll do the same thing for the Red Hot Chili Peppers song. So here I'll pass the relative band energy ratio array, and here we'll set this color equal to red, and finally we'll do a plot.show. Now obviously if I go on and press enter, I get an error because the t is not defined. We don't have a value for that, so I should implement that. first thing, I want to just like bring up one of these boxes here so that I can define T. So first off, I need to define frames, and this is going to be equal to range, and I'll get the length of the, say, bare Debussy, the band energy ratio array for Debussy, and the length is going to be equal for Debussy and the Red Hot Chili Peppers, so I can use just one. Okay, so here now I have like this value for this variable frames, and now I can move on and implement T. And here what I can do is use Librosa, and here Librosa has a nice utility function called frames to time, and what it needs as arguments is the frames, and then I should specify the hop length, and the hop length I think we specified up here as a constant called hop size, which is equal to 512. So totally traditional number for that. Okay, so we'll do this. Okay, and so here what I get is basically like the value of time at each frame. So let me show you what I mean by that. So here T is an array, and the length of T is equal to 1292. So these are all like the frames, and for at each frame we're just like converting from just like int to like the relative time given the hop length that we are using. Now that we have T, we can move on and plot our band energy ratio for the two songs. So, and as you can see in blue, we have the band energy ratio for the Debussy piece, and in red, we have the one for the Red Hot Chili Peppers song. And there's a stark difference between the two. And basically, the band energy ratio is way higher for the Debussy piece than the Red Hot Chili Peppers ones. And that's usually the case. It's something that you find quite often when you compare classical music with rock music. And that's because in classical music, most of the energy is concentrated in the lower end of the spectrum, whereas in rock music you have a more balanced distribution, and that's probably has to do with the fact that there are a lot of like noisy sounds like snares or like stuff like this that just like provides energy or offers energy in the higher end of the spectrum in rock music. Okay. So by now you should be able to have, well, you should have like a very deep understanding of band energy ratio and how to calculate it from scratch with Python. And you probably also have an idea of how band energy ratio like works in different genres, which is great. So that's all really for today. So next time we'll be looking into the remaining two frequency domain audio features and how to like implement them, but we won't implement them from scratch, but rather we'll be using Librosa for implementing them. So if you've enjoyed the video, please leave a like. If you haven't subscribed and want more content like this, please subscribe to the channel, and I guess I'll see you next time. Cheers.